All right, we are moving on this week to some kind of new stuff. We finished up permutations and combinations last week with that test. Don't forget that test is due by today at 4 p.m., so make sure you get that uploaded, and I'll get those graded very soon. We're going to this last unit we're going to do for Algebra 2 is actually going back to what we left right before we left actual school. So we're not going to get to cover all of that unit, but we're going to just kind of cover some of the basics, and then you'll make up for it when you get to pre-cal your senior year. So inverse functions. So we kind of left off with exponential stuff, and we're going to switch gears a little bit and talk about an inverse function. The functions f and g are inverses. If, and remember this notation, let's make this bigger. This notation f of g of x, we've talked about that before. If that equals x for all x in the domain of g, and if g of f of x equals x for all x in the domain of f, then f and g are inverse functions of each other. That's one way to define it, and we'll see kind of how that works here in a little bit. But what we'll use more often, this is kind of the important part, is that if you want to find the inverse of a function, well, if that function has an inverse, you can find it by writing y for f of x, interchanging x and y, and then solving for y. And the inverse of a function, so if we call a function f, we use f to the negative first to say its inverse, and that's read as f inverse. So if you ever see f negative 1 like that and then equals an equation, that's f inverse. It's not f to the negative first power. Okay, and just keep in mind too, like when we talk about inverse functions, think about like what inverse means in math. We have inverse operations, so like addition and subtraction are inverse operations, multiplication and division, squaring and taking a square root, right? So now we're talking about doing the inverse of an entire function, not just one operation, but of that whole function. Okay, so to find an inverse, kind of what we just said here in the little box part, if I'm given the function f of x equals 4x minus 7, I want to find the inverse function. Okay, so what we do, we're going to take our f of x equals 4x minus 7, and I'm going to replace the f of x with a y. And we've talked about this before. Remember, f of x is just another way to say y. So I'm going to rewrite that as y equals 4x minus 7. Okay, then the next part says interchange x and y. So basically, I'm just going to take the x and the y, and I'm going to trade their places. So instead, I'm going to write it as x equals 4y minus 7, right? Just switch out the x and the y. That's how we're making it be the inverse. And now, if I want to put it back into a function form, I want to solve for y, right? So we interchanged them, and now we're going to take that and we're going to solve for y. Oops, if I can spell solve. So if I've got x equals 4y minus 7, I'm going to add 7 to both sides. So I get x plus 7 equals 4y. And then I'm going to divide everything by 4, right? So that will give us a y equals, and then there's a 1 in front of that x, so I could write it as 1/4 x plus 7/4, right? So then we get our inverse function, or f with a little negative 1 of x would equal 1/4 x plus 7/4. Ta-da, there is our inverse function. Okay, if you wanted to leave it with just over 4, we could have also written it as with just the 4 on the bottom. So you could do x plus 7 all over 4. That's totally fine if you want to leave it in that format. I just put it in slope-intercept form because that's what we're used to. Okay, so I had a linear function, found the inverse, I still got a linear function. That's normal. Okay, so that's how to find the inverse of a function. Now we're going to see we've got f of x is 2x plus 3, g of x is 1/3 x minus 2. We want to know, are those inverses of each other? Now, there's two ways you can figure this out. What most people do, what I think most of you will do, is just take one of the functions and find its inverse and see if it matches the other one. That's probably the easiest way to go about this. So I'm going to take f of x and it's 2x plus 3. And again, I'm going to write that as y equals 2x plus 3. And now I'm going to switch the x and the y, right? So I'll get x equals 2y plus 3. And now I want to solve for y. So I'm going to subtract 3 on both sides. I get x minus 3 equals 2y. And then I want to divide by 2. So I could leave it as x minus 3 over 2, but they've got it up here for g. They've got it in slope intercept, so I'll do the same. And I get y equals, that would give us 1/2 x minus 3 halves. Okay, so now I want to compare it to that. This would be our g of x, right? If it's the inverse. I got 1/2 x minus 3 halves. They had 1/3 x minus 2. So that means no, they are not inverses, right? Because when I found the inverse of 2x plus 3, it is not 1/3 x minus 2. So they are not inverse functions. Okay, that's one way to go about it, using that kind of box definition that we did up there. The other way, just to show you, just in case you like this other way better, if you'd like to try a different method, is we can use this part that's up here, this definition where we talk about f of g of x and g of f of x. So you can plug one function into the other and see if you just get x. If you do, then they're inverses. So I'm going to do f of g of x. So my f of x is 2x plus 3, so 2, but then instead of x, I'm going to plug in g of x. So I'm going to plug in 1/3 x minus 2, and then I finish off with plus 3. So there's that 2x plus 3, except instead of x, I'm plugging in what the function g is, right? That's my 2 there. Okay, and then I can solve that. So this will give us 2/3 x minus 4 plus 3, which is 2/3 x minus 1, and that is not just x, right? If they were inverses of each other, then when I simplified that whole process, this would just end up being just x. Since it's not, then they are not inverses. Okay, to kind of show you, well, let's see if I have room here. If I show you up here, if I do the other method on example 1, I can take that, let's see, f of x is 4x minus 7, right? And I'm going to plug in the inverse. So I would do 4 times, let's see, 1/4 x plus 7/4, and then minus 7, right? So plug one function into the other. Well, 4 times 1/4, that's just 1. Oops, sorry, I should write that as f of g of x. Or we don't really know, f of the inverse. F of f negative 1 of x. We'll write it that way. 4 times 1/4 is 1x. 4 times 7/4, well, those 4s would cancel. That'd be plus 7, minus 7, and we just end up with x. That means that they're inverses. Okay, so one of two ways. You can just find the inverse of one of the functions and see if they match, or if you want to do the composition version, you plug one function into the other, and that will tell you if it's an inverse. Okay, that's how we can find inverses and see if functions are inverses of each other. Now let's kind of talk about the inverses on a graph. So on this graph here, we've got, let's see, the blue one here is f of x, and it's already graphed for us. And then let's get red, we match. The red function here is g of x. Okay, so notice kind of how they look and what you notice. And the other thing I want to do here is we're going to put some points on our lines. So here I've got, see, that's 0, 2, right? I've got another good one here. That's 2, 3. I'm going to pick another point there. That's 4, 4. And maybe I'll pick one more here. That one is 6, 5, right? There's the blue points. And then I'm going to pick some points on my red function, or on g of x. So here I've got 2, 0. That one is at 3, 2. Again, that same point is here because I cross, right? So 4, 4. And then I'll go one more up here. That one is 5, 6. And hopefully you kind of notice something on those points. When I put 0, 2 right here, if I look at that same spot on the other function, I get 2, 0. Here's 2, 3, 3, 2. 4, 4 and 4, 4 are the same. And then 5, 6 and 6, 5. So see how in every point on the other function, on the inverse function, the x and the y value are switched. That's why up here when we find our inverse, we can do it that way, is by switching the x and the y. Okay? So on a graph, you'll always see the x and the y points switch places. Okay, the other way to see that is these are inverse functions. They are mirror images of each other if you look at it along this line, y equals x. So if I draw in this guy here, y equals x just looks like that. Has a slope of 1 and an intercept of 0. But it is reflected. So if I take one function and I reflect it over that line, that y equals x, I will get its inverse function. Okay. Okay. Something else we've talked about before, one other way to tell if a function has an inverse, because sometimes it doesn't have a inverse function. It always has an inverse, but not necessarily an inverse function. And that's with the definition of something we talked about before called one-to-one. I don't know if you guys remember talking about that. It's kind of like deciding if something is a function, but it's called a one-to-one because it's the opposite way, right? So for instance, if I have a function, if I just make it like this, right? If I do that horizontal line test and look at them, it's going to have an inverse function because it passes the horizontal line test. It only crosses through one point at a time. So yes, this has an inverse function because it's one-to-one. If I look at a graph, say like this, a parabola, that is a function, but if I do the horizontal line test, it does not pass. So it does not have an inverse function. And what happens is when I do the inverse here, it looks like, you can do an inverse, but it looks like this. And that's not a function. So it does not have an inverse function. It has an inverse, but its inverse is not a function. Okay, so there's one other thing. We won't do a whole lot with that right now. You'll do more with it in pre-cal, but just so you kind of understand that whole one-to-one thing. Okay, so looking at our horizontal line test, that's what it just says there. A function has an inverse if and only if every horizontal line intersects the graph of the function at most one point. In other words, it's one-to-one. Okay, so let's do that a few times here with a graph. So this first one, we want to graph h, the function h, and determine whether it has an inverse function. If it does, we want to graph the inverse by reflecting it across that line y equals x. Okay, so let's start with graphing our function h, 3x minus 2. That's a linear equation, right? Y equals mx plus b, or if you want to think of it as y equals 3x minus 2. To graph that, we plot our y-intercept, which is negative 2. And then we're going to use our slope, so I can go up 3 to the right 1. I'll go all the way across the graph, or I could go down 3 to the left 1, right? So then if I draw in my line there, ooh, that was not a good line. Try that one more time. Draw in my line. That's a little better. That is our h of x, right? Okay, so now if I look at my horizontal line test, right? So now I'm looking at if I put horizontal lines across this function, does it ever cross more than once? The answer is no. So yes, it does have an inverse function. So h does have an inverse function. Okay, so now we want to find, or we want to graph that inverse function, right? The easiest way to do this is to make a table of values for your original function. So for my h of x, if I make my x and y values here, and just pick all the points that I already plotted on my graph. So this one down here, that is negative 1, 1, 2, 3, 4, 5, negative 1, 5, right? Negative 1, 5. And then, and this is like our x and y, right? Then I've got 0, negative 2. I've got 1, 1, 2, 4, and 3, 7. Right? And all I'm doing is writing down the ordered pairs for all those points that are on my line, right? Now to graph my inverse, all I need to do is switch all of those points. Oops. So for my H inverse of x, I'm going to make my x and y chart, and I'm just going to take all those ordered pairs and switch them. So this is going to become 5, negative 1, negative 2, 0. 1, 1 is going to stay 1, 1, 4, 2, and 7, 3. And I'm going to plot those points on my graph to make my inverse function. So 5, 5, negative 1, negative 2, 0. Over there, right? 1, 1 would still be here. Did I do 5, negative 1? I did. Oops, that's my fault. Maybe my line looked off. That should be a negative 5, right? This should also be a negative 5. Okay, that works better. So it should be negative 5, negative 1. There we go. You guys would have fixed me if we were in class, right? Wait, Smack, you missed a negative. Okay, then we've got 1, 1, then 4, 2 goes here, and 7, 3 goes there. And then we can draw in that function. And there's our inverse. That's our h negative 1 of x, right? And again, you can see that kind of line that goes through the center that's reflecting, or that's what shows your inverse, right? Okay, last part, let's actually find the equation for our inverse, right? So to do that again, we can take our original function, so h of x was 3x minus 2. I'm going to write it as y equals 3x minus 2. We're going to switch the x and y and then solve for y. So I'll switch them. So x equals 3y minus 2. And then I'm going to solve for y. So that'd be x plus 2 equals 3y. And then divide by 3, get 1/3 x plus 2/3. So our inverse function, h negative 1 of x, is 1/3 x plus 2/3. And you can kind of look up at the graph and see that that matches. Our y-intercept looks at about 2/3, right? And then my slope, I'm going up 1 and to the right 3. So there is our inverse function. Ta-da! With its graph. Okay, lots of different things you can do there with inverses. All right, let's try one more of these. This time we'll do one that's not linear, just so you can see it doesn't have to just be a y equals mx plus b. It can be different kinds of equations. So here, it's already graphed for us, right? We've got a graph of the function f of x equals x cubed minus 1. Again, we want to know, does it have an inverse? And if it does, we're going to graph it. So it's already graphed for us. To decide if it's a function, I'm going to use, or to decide if it has an inverse function, I'm going to use that horizontal line test. It passes, so that means it does have an inverse function because it passed our horizontal line test. And now we want to find that inverse. So remember, again, we're going to label our points to start with, right? So here's f of x. And let's do our x and y. So I'm going to just pick all the ordered pairs for these points. So that's negative 2. Let's see if I get my negatives right this time. Negative 2, negative 9, negative 1, negative 2, 0, negative 1, 1, 0, and then 2, 7. Okay. And now we're going to take that table and find the inverse. So now I want to just switch all of our x and y values. So this would be negative 9, negative 2, negative 2, negative 1, negative 1, 0, 0, 1, and 7, 2. And now I'm going to plot all of those points. So we go negative 9, negative 2, is here. -2, -1 is here. -1, 0 there. 0, 1. And then 7, 2. You can see how it's kind of making the same shape, only the other direction. And then it's got kind of this curve here in the middle. So we're going to try to make that same curve in our graph, but just do your best. So I think it's helpful if you kind of turn it sideways and it's easier to draw. It kind of makes a curve through there, right? Same general shape. And there's our inverse. And again, if you want to see it, you can kind of think about that. Y equals X line is what it reflects over to find the inverse. Okay, and then down here, our last part, we want to actually find the equation of it. So our original function, f of x, is x cubed minus 1. We want to find our inverse, right? So I'm going to replace that with a y. Say y equals x cubed minus 1. And now to find my inverse, I will do x equals y cubed minus 1. And then we're going to solve for y. So add 1 to both sides. X plus 1 equals y cubed. And I don't want it to be y cubed. I want it to just be y equals. To fix that, I'm going to take the cube root of each side. So then I get the cube root of x plus 1. And the cube root of y cubed is just y. So then our inverse function, f inverse of x, is the cube root of x plus 1. Ta-da! There we go. Okay. All right, so there's kind of a non-linear example, so you see how that works with the graph and the function. Okay, right before we left school, like I said, we were working on exponential functions, right? We had done a little bit with graphing, a little bit with some kind of solving stuff, but basically, if we do the most basic exponential function, that y equals 2 to the x, if you remember, that looked like if I do 2 to the 0 power, I get 1. If I do 2 to the first, I get 2. If I do 2 squared, I get 4. 2 cubed is 8, and it starts getting really big, right? And then negative numbers, we found that made us have fractions, and it just gets really close to that line but never crosses it. So our exponential function looks like that, right? Now, if I do that horizontal line test, I'll see that this does have an inverse function. But what does that look like? So let's kind of think about it. If I had y equals 2 to the x, well, we said to find the inverse, I would switch x and y, right? So I want to find my inverse function. So I would do x equals 2 to the y power. And now I want to find, or I want to solve that for y, right? So how do I get the y out of the exponent? And this is where we kind of get into another new set of functions, and we'll do a little bit with it. We won't do nearly as much as normal. But basically, we need a new type of function here. And what it is a logarithm. So we've got exponential and logarithm, and those two operations, or those two functions, are inverses of each other. So the inverse of exponential is a logarithm. If you remember, we did some stuff with logs first semester, just some very basic stuff. And now is when we really get into what logarithms can help us do. But we'll only be able to do a little of it. But that's one really important thing to remember, is that inverse of exponential is logarithmic, or inverse of exponential is, sorry, a logarithmic is exponential. You'll get into a lot more of that in pre-cal. Okay, so from there, before we do more stuff with logs next week, I do want to kind of remind you of the stuff that we covered first semester. Some of you will remember this well, some of you it's been a while. You can look back at your notes in your binder if you've got it with you, and find the old stuff over logarithms we did if that helps. But I'll go through it. Okay, so the first thing we did was switch between exponential and logarithmic form. And we want to be able to do this to help us solve problems later. I gave you a little rhyme, if you remember it, to do kind of these two parts. I always said the base becomes the base, and the other two Can you finish it? Play switcheroo. I don't really know how to spell switcheroo, but hey, switch, oops, not like that. Switcheroo. Okay, so if that helps you remember, you can say it that way, right? But here's how that works. So if I've got log base 2 of 32 equals 5, remember that's how you read that, then to switch it into exponential form, because that's what we want to do here, I'm going to make the base of the logarithm be the base of my exponential. So 2 is my base. And the other two numbers, the 32 and the 5, will switch places. So the 5 becomes my exponent, and the 32 becomes the result. And you can kind of check it here. 2 to the 5th power is 32. That is a true statement. You can also remember that the answer to a logarithm is always an exponent. Right? That's another kind of important thing to remember here. The answer to a logarithm is an exponent. So anytime it says log equals something, that equals number is the exponent. Okay. All right, so we'll do the next couple here. A base becomes the base, so this would be 3 is our base. The exponent would be 2, because that's the answer, and then equals 9. And that is true, 3 squared equals 9. Next one, 7 becomes the base. The exponent would be our 1/2 equals the square root of 7. And that one we know, we've done that a ton. When we have a rational exponent, the 1/2 means it's the square root. Number on top is your exponent. Number on bottom is your index, right? But you don't have to write those because they're a 2 and a 1. Okay, and last one, 3 becomes my base. -4 is the exponent equals 1/81. We all know a negative exponent means we have to move it to the bottom of the fraction, so that's how the 81 gets on the bottom. All right, now we're going to do it the other direction. So now we're going to change it from exponential to logarithmic form. So we're starting with exponential, switching to logarithm. But same thing applies. The base becomes base, the other two switcheroo. So now I'm going to do log, and my base is my base from my exponential. So my base is 4. And remember, that's a smaller number. It's like a subscript. So you write it down below the G. Of, and then I'm going to switch the 3 and the 64. So of 64 equals 3. The answer is the exponent, right? Next one, the log, my base is 9 of 27 equals the exponent, which is 3/2. Okay, log, my base is 10 of 0.01 equals my exponent, which is -2. And last one here, my log base is 16 of 1/8 equals the exponent, which is -3/4. Okay, there's no real computation you have to do there at all unless you want to check your answer. You are just switching between one form and the other. Okay, and where this can come in useful is then it helps us solve or simplify logarithmic expressions or evaluate them, right? On all of these, your answer should just be a number, because remember, your answer is your exponent, right? Okay, so one way to kind of think through these, we did some of these before, is if it helps, you can write equals X on here, or equals question mark. I tend to like to use a question mark because we're not really solving an equation there, we just want the answer. So if I change this to exponential form, that would mean 6 to what power equals 36. Well, 6 to what power equals 36? That's 6 squared. So our answer is 2. Ta-da, because 6 squared equals 36. We do the same thing every time, right? So equals what? So then 2 to what power would equal 16? Well, that has to be 4, because 2 to the 4th is 16. And you can just start, if you can't figure it out, put it in your calculator. 2 times 2, and just do it until you get the answer, right? So our answer there is 4. This would be 10 to what power equals 100? Oops, not 1,000. There you go. So that'd be squared. So our answer is 2. This one, we've got a fraction, so 3 to what power equals 1/9. Remember, in order to get a fraction, that means it's going to have to be a negative exponent, right? And then to get the 9, we'd have to square it. So it'd be 3 to the negative second equals 1/9, which means our answer is -2. This one, we'd have 7 to what power equals 1? Well, the only way I can get 1 is if I make that exponent a 0. Anything to the 0 power is 1, so right into there, 0. And then this one, we've got 6 to what power equals 6 to the 5th. Well, think about that one. 6 to what power equals 6 to the 5th? The only thing that makes sense there is 5, right? 6 to the 5th equals 6 to the 5th. So our answer there, 5. Okay. All right, so there's kind of some review of the logarithm stuff that we did last semester, and then we learned a lot about inverse functions and how those work. Big key takeaway, inverse of exponential is logarithmic, right? Or vice versa. How to find an inverse, what it looks like on a graph when we graph an inverse. I have a very short exit ticket for you guys to do today. It'll be on a Google form. There's a link to it in your homework. Go and complete those couple questions. And then on the next class this week, you'll get a homework. It was kind of like what we did last time, but it'll have some guided examples and then problems to do on your own. Okay? Let me know if you have any questions on this stuff, if it doesn't make sense. Otherwise, I will hopefully talk to you guys in a few days.